All right, we started section 4.2 about area last time, and we had just a little bit left to do. We had taken a look at an image. This was the one, and we were talking about finding the area under this curve, and we kind of split it into these rectangles, and we said, hey, you know, if we looked at these from the left-hand side or from the right-hand side or from the midpoint as the height, we could create these rectangles, we could find this area, and it would be an approximation, and the more and more rectangles that we do, the better the approximation would be. That's where we left off. What I need to show you still left on these is how we actually calculate those areas. So what I want to do is, instead of labeling these as A and B, I'd like to label them as some notation that looks a little bit more like what we've seen in this section. We're going to label these as X0, X1, X2, X3, and X4. And as you can tell, what happens as we're labeling those is it starts to look like this sigma notation that we were doing last time, right? So what I'd like for you to also notice is that the width of each of these are the same. That wasn't very good. Let's try it again. That's better. The width we would call the change in the x values, or delta x, is equal to, and you can find each one of them, right? It's x1 minus x0, or it's x2 minus x1. But in reality, we could also say in general that it's x4, the end point, minus x0, the starting point, and then dividing by 4. All right, so on this one in particular, and that's true for all of our areas, or all of our rectangles that we're doing that. I'm going to shift this up here. I realized I didn't put that in quite the right spot. That's okay. Here's a good spot. Okay. So on this one in particular, we're trying to find the left-hand rectangles, right? The areas where the left hand is the end point that we're using for the height. So just for the sake of reminding ourselves that it's left hand, I'm going to call this L of x. And what we need to do is we need to find the area of each rectangle. Well, you know how to find the area of a rectangle. It's length times width. But the widths are all the same. They're this delta x value that we're going to calculate, right? So the width delta x of the first one multiplies by the height of the rectangle on the left-hand side. So this is the function value at x0, right? This right here is f of x0. Okay? And we're going to do that for each one of our rectangles. So the second one is delta x, and it's the function at x1, the y value at x1, plus delta x, and it's the y value, or f of x value, at x2. And the last one is delta x, and it's the f of x value at x3. Now notice there's no f of x4, because we didn't use that height for any of our rectangles on this particular calculation. But it's also probably worth noting that each one of these have delta x in them. So it really would actually be a lot simpler, algebraically, to multiply by the delta x after we've simply added all these heights together. So we can add f of x0, f of x1, f of x2, f of x3, and after we add them, we could actually multiply by the width of the rectangle. Now we can use this very same idea on our right endpoints. Our right endpoints will have the same x1 through x4 value. In fact, I think I'll copy and paste those as a reminder to us. But the difference on this one is that I'm using the right-hand heights. So again, as a reminder, I'm going to call this r of x. And since I did this before, I think we're okay probably with not writing it out all of the delta x's times them. This is delta x, and I need the height of the right-hand endpoint. So the first right-hand endpoint is actually f of x1. The next one is f of x2. And then I have f of x3. And I have f of x4. Now, I would be remiss, that would be, like sad if I didn't mention to you that this has another form. We're not really going to use this per se, but it's the connection with this section of material that we saw from last time. What you should notice then here is that we're adding a bunch of things together. It's a summation, or a sigma, from I equal 1 up to 4 of our f of x sub I. That is in general what we're doing on these. In practice, right, in actual practical terms, we can use the formula above, but this does consolidate each time. Now we'll talk in sort of vague terms a little bit about what we're doing on this next one for the midpoint, but we won't write down a formula for it. Sorry, I'm trying to get this to cut it and go away. So if we take a look at these values over here, the difference between this one and the last two is that none of those x1, x2, are actually the heights that we use. We have to find the midpoints to find the heights, and there's not a real standardized notation for how to write this like there is for the left endpoints and the right endpoints. So we don't really have a formula that we're using, but just suffices to say that we are going to use the heights of the midpoints instead. All right, so we absolutely need an example to make sense of this, I think. So our example that we're going to do is a very simple function. It's a quadratic. It's f of x equals 2x squared plus 5. Even without a calculator, you probably have an idea of what this looks like. It's a parabola opening upward at a height of 5. So it looks something like this, right? Well, that was bad. That's a little bit better. Now, we really don't need this whole picture. Take a look at the interval it gives us. It's only an interval from 0 to 2. So while this whole picture is accurate, it's also not necessary, nor is it actually very helpful. So I'm going to write out my picture, and I'm going to draw it a little bit bigger, but with only the portion of the graph that I need, namely the portion that's on the right-hand side. So it looks something like this. And remember, we're really not concerned with it being drawn to scale. And to be honest, you don't have to actually draw the shape either. However, it is often very helpful to at least draw the number line that you're breaking apart. So we're breaking this apart from 0 to 2, so it looks something like this. And it does, in fact, say, like our example that I drew before, that we're using n equal to 4 or 4 rectangles, okay? So this is 1 and this is 2 to go from the interval 0 to 2, but I need to divide it and subdivide it into rectangles that give me 4 rectangles. And I'll use decimals, but you could certainly use fractions here too. This is 0.5 and 1.5 for the in-between locations here, right? So we're supposed to find the left-hand rectangles, the right-hand rectangles, and the midpoint. So we'll start with the left hand. So you might take a look first at noticing what is the width of each one of these, right? What's the distance right here? Well, the distance is 1/2. So that's my delta x out in front. It's 0.5. And it's the same delta x value whether I'm doing left-hand endpoints, right-hand endpoints, or midpoints, okay? So it doesn't make any difference. That's the width of all my rectangles. And then I need the function values that are on the left-hand side. So I start with the leftmost endpoint. Now, it's not labeled here right now, so I might want to put that in just as a reminder. I'm starting at 0. So on a left-hand endpoint, on my interval from 0 to 0.5, 0 is the left-hand side of that. So I need f of 0. And then I need everyone after that of those hash marks I marked. So f of 0.5, f of 1, and the last one is f of 1.5. Again, notice I don't need f of 2 because the interval from 1 to 2, from 1.5 to 2 has the left-hand endpoint as its height, which is the interval or the height at 1.5. Okay, you can find all of these in your calculator. In fact, if you wish, you're welcome to put this equation into your calculator into y1. You can use your table to find the values that you're corresponding to over here. There's actually a really cool trick too. It works better if I were in person to show you. But you can use another feature inside your calculator to calculate these sort of in the main screen. It's not necessary, but it's kind of a fun feature. At any rate, when we put this in the calculator, make our calculations and so forth, or do it by hand if you wish, you're going to get 13.5. To do the right-hand endpoint, it's very similar. I have the same 0.5, but I don't start at f of 0 because I use the right endpoint. So on this one, I start at f of 0.5, and I have f of 1. F of 1.5, and F of 2. Right, those are my 4 endpoint values that I have. And again, with my calculator, that gives me 17.5. The midpoint rectangles are the most interesting. They're the most interesting because they don't use the interval endpoints that I've marked so far. They use that midpoint, right? Now, they still have a width of 0.5. Okay, they're still the same width because they're still the same rectangles. They're just measuring the height at a different location on the rectangle. So what I need to do is I need to measure my height halfway in between each of these values. I'm going to mark them in red to distinguish them. So halfway in between 0 and 0.5 would be 0.25. And between 0.5 and 1 would be 0.75. Between 1 and 1.5 would be 1.25. and then between 1.5. And then halfway between, like I was saying, 1.5 and 2 would be 1.75. So over here, we're going to have all these functions at those red values now. So I have f of 0.25. I have my f of 0.75. I have f of 1.25. And I have f of 1.75. And again, with your calculator, all that can be done by the calculator itself. If you are using the table and it's giving you values, these are the ones going to give you really nice values. But if it gives you values that are like long repeating decimals, keep a few of them. You're going to round to a couple decimals at the end usually, something like that. Keep a little bit more than it's requiring you to round to at the end. So if it says round to 2 decimals, maybe you keep 4 through the problem, right? And then you round off to 2 at the end. That's kind of your rule of thumb. And the problem will tell you how many to round to, so don't be concerned about that. And then I have, as the final answer, 15.25 for this one.